In an ever-connected world, scientists are increasingly working together to solve the biggest issues facing societies today.
There's huge potential here.
From health to energy and sustainability.
You're talking massive climate impacts.
This week on 10 Things to Know About, researchers are reimagining waste and working towards a circular economy.
The dairy industry in Ireland is a big business and it produces a lot of wastewater, which is expensive to treat. Researchers are investigating ways of turning this no-value waste into high-value products. Paul Bulger is focusing on the circular economy, leading to a more sustainable society.
We live in an economy that is based on take-make-waste production systems. So we take resources, we make goods and materials, and most of those goods end up in our waste bin or in landfills. So to really create a sustainable society, we not only need to move towards zero carbon, we need to move towards circular production systems. So this is a huge opportunity for Irish business. Within this project, we focused on dairy industry processing wastewater, which is about 15 million tonnes of this kind of wastewater every year. So that's 2 litres of wastewater for every litre of milk you drink.
Wow.
So it's a lot of material. But it's a treasure trove of valuable constituents. We've got carbon and nitrogen and phosphorus. What we want to really look at is how do we take these wastes and make them into resources?
Yeah, because it means like rethinking about how we make stuff so that it doesn't just have one purpose, but actually has a life after its use.
We all know the leadership of the Irish dairy industry in terms of innovation, but there could be innovation around the circular economy as well.
Wastewater from the dairy processing industry contains high levels of nutrients and is treated extensively to prevent it from polluting natural ecosystems. Niall O'Leary is developing systems that not only treat the wastewater, but also creates eco-friendly bioplastics in the process.
The system as it is focuses on just breakdown and treats the material coming in very much as a waste and a problem. And it costs a lot of money. So what we're trying to do is re-envisage the waste as a potential source of nutrients. Because bacteria have been around for so long and evolved, some of the things that they can do is to convert carbon into value-added products that we can actually use ourselves. So one of them would be polylactic acid that we come across a lot in terms of plastic cups and that kind of stuff. What we're looking at is a different type, but it's a very particular type of polymer because it's all made of lactic acid. So it's a internally accumulated material that the bacteria uses to store carbon and use later, but we can then collect it out of the cell and use it as a material.
So tell me, how do you go about creating these biopolymers?
So what we try to do is use reactors to train the community of bacteria that are already present in wastewater treatment systems. And how we train them is we give them a pulse of food at the very beginning and then we starve them for a very long time.
Poor bacteria.
Poor bacteria. But what they do is only the ones that are good at storing carbon to survive that starvation period, they'll persist in the reactors and the rest will disappear.
Is that carbon within them a polymer at that point?
It is, it's polyester.
Okay, so they actually make it in them by storing it.
Yeah.
Amazing.
It is amazing. Yeah.
Thank you, bacteria. You're so clever.
Yeah.
After the wastewater has gone through the reactor, Niall can assess what type of bioplastics the bacteria can make.
There have a range of applications, from very simple applications like replacing plastic bags and that kind of end of house, right up to medical implants, heart valves, really high-tech applications. And we're currently producing the lower end, I suppose, the shorter chain polymers, but we'd like to broaden that.
With the global demand for plastics, the potential for this technology is huge. Amazingly, it doesn't end there, as project partner Marcel Janssen explains.
We get that wastewater from Nile, and that is full of nitrogen, phosphorus, and lots of plant nutrients. We try to capture that by growing plants on it, and it's a very special plant called duckweed.
Duckweed, never heard of it.
Be commonly growing on slow-streaming streams and ponds, lakes, so very common. But it is actually quite a special plant. It's an extremely fast-growing plant. It would have doubling times of about 2 days, and therefore it takes up very fast those nutrients. What else is special about it is That plant is also chock full of protein, about 30%, 40% sometimes of that plant is protein. It's the same protein as, for instance, in soybean. So the plant cleans up water, but it also generates value from, for instance, wastewater.
Current treatment systems lose valuable nutrients, releasing nitrogen into the atmosphere and converting phosphorus into a sludge. Capturing the nitrogen and phosphorus with duckweed means it can go straight back to the farm as a high-value feed or fertilizer.
This is the final duckweed. Duckweed simply dried and ready to be used as in a feed, for instance.
Could I eat it?
This is clean duckweed, so you're absolutely fine to eat it. There's not a lot of taste, but there is a lot of protein in it. It's quite healthy.
I don't know if I'd eat a bowl of it, but
30% protein.
maybe I would. This technology can easily be integrated with existing treatment systems. Wastewater is pumped to the top and naturally flows down through the duckweed. Each square metre of duckweed can clean 10 litres of water a day, so stacking the system maximises efficiency.
It's the most boring plant you can imagine, and I say that as a duckweed researcher. But what it can do is truly amazing, and it can really help us, to change agriculture. But because I'm a firm believer we need a strong agricultural sector in this country. We simply need to change the way we farm. And there's ample scope to work with nature to make Irish farming a leader in sustainability.
Farmers are performing a delicate balancing act, trying to reduce emissions to meet new targets while putting food on the country's tables and not losing a livelihood at the same time. As we try and find novel uses for waste, could slurry be part of the answer? Farmers collect manure to create slurry, a natural fertilizer. There's often an excess at the end of the season. Fiona Thorne is exploring sustainable uses for this slurry. How can slurry be used to create fuel?
So the technology is called anaerobic digestion. And what happens is that you have feedstocks, one of them, which it can be, is slurry, coupled with other feedstocks such as grass or grass silage. And they're put into a vessel, into a metal tank, and they are co-digested in the absence of oxygen to provide energy out the far sides. And that energy can be used for multiple different uses. It can be used for transport, it can be fed into the gas grid and used for the gas which is used every day to heat our homes.
Biomethane is a renewable replacement for natural gas and is already widely produced across Europe.
The difference between Ireland and our counterparts in mainland Europe is that there has been big policy incentives there to produce the anaerobic digestion industry. That gap between the price of natural gas and the production of renewable gas, it needs incentives there.
These anaerobic digestion plants sound very interesting, but they're not viable for every farmer. I'd like to hear their views on it.
I've done a bit of research into it, and I know the science behind it, I know how it works, and I know it works in other countries. So, yeah, it's definitely something I'd be interested in.
It's a case of show me the money. I mean, if it's economically viable and it stacks up, they'll jump to it. You'd have a queue a half a mile long.
Is it something that you'd be happy to have on your farm or near your property?
Yes, obviously you're not going to put it up against your house or anything, but once you have it out on the farm, and it's just another building, really.
Do you think that the cliche of farmers being resistant to change is not true?
Yeah, I do. I really do. They're progressive, they're environmentally conscious about things going forward, as much as anywhere, they're in touch with the land.
Do you think it's important for Ireland to generate its own energy?
Oh, it's vital for us. The more renewable energy we can have, the better, and the more consistent sources. I mean, if we can get a source that has a consistent and reliable and predictable output, sure, it's wonderful for the grid and it's wonderful for our system.
Ireland is among the countries in Europe with the highest potential to produce biomethane. In order to see how feasible anaerobic digestion plants would be, Maurice Deasy gathered data from 1,000 farms covering all types of agriculture.
If this system is to work and to roll out across Ireland, it needs to be profitable for the farm so that it's viable and it'll be continually viable. What's important is we're looking at a farm level. We're using real data from farms to say, for each size of farm, how will this work out? Will it be economically viable at the different scales and for different enterprises across the country?
It's all about optimizing land use for the environment and for profit as well.
Yeah, financial stability is linked in with sustainability, but we're also looking at how would multi-species swards and grass clover swards fit into this system, and that's very good for biodiversity. We could actually have the same animals on a smaller area and produce more grass to produce energy. There are farms that are more vulnerable, and having an alternative option might be very viable.
As slurry and silage are heavy and costly to transport, various scales of AD plants would need to be built across the country. However, the biogas from these plants could produce up to 10% of the national grid.
We're talking about between 150 and 250 plants. It's not producing all of our energy demands, but it's a step on the way. And what's important for agriculture is if we can reduce our emissions while generating a renewable energy, that's an important sustainability win.
It comes as no surprise that waste plastic bags are seen as one of the worst environmental offenders. But tracing the history of the plastic bag through time reveals an altogether more complex story. It's 1933, and two chemists are working in a lab in Norwich in the UK. Trying to react two polymers together, their machine suffers an air leak, and a strange, white, waxy substance is produced: polyethylene. Unbeknownst to the pair, this accidental discovery would go on to have huge implications for both plastics and the planet. Fast forward to World War II. The British military kept polyethylene a closely guarded secret, using it to insulate cables on newly developed radars and playing a crucial role in spotting the enemy at a distance. Post-war, the plastic revolution led to an explosion of interest in this material, and in 1959, a Swedish engineer named Sten Thulin created the first plastic bag using polyethylene. Lightweight, durable, and able to be used again and again, he always carried one in his pocket, and ironically, invented the plastic bag to protect the planet by replacing paper bags which needed trees to be cut down. But the low-cost mass production of plastic bags meant that what was originally intended as being multi-use in theory turned out to be single-use in practice, piling up in landfills and polluting our seas and lakes. They've wreaked havoc on the environment. From being synonymous with our make, take, dispose linear economy, to the recent introductions of plastic bag levies and reusable carriers, the story of the plastic bag really has come full circle. See you next time.
Raw materials have been mined for millennia, and it's still a vital industry today. As we aim to create a circular economy, the focus is not just on what we take out of the ground, but how we manage the entire life cycle of minerals and metals. I'm at the Avoca mine to speak with Owen McGrath about mining raw materials.
We've a really long history of mining in Ireland, from right back in the Bronze Age with old copper mines and right up to modern times. We're here in Avoca, which was one of the biggest mines in Ireland for a long time, and it operated for over 250 years, from the early 1700s right through to early 80s. In the past, the rock was taken out and it was crushed, and then it was processed through a chemical process whereby the metal was extracted, and usually then whatever was remaining was just dumped in the locality.
These large piles of rock are known as spoil heaps. There are still metals and minerals in the rock, partly because the technology at the time wasn't able to extract them.
In a modern mine, you don't get waste piles like this. Waste is much more tightly controlled. A lot of the waste goes back underground and is used to refill the mines, and we also have a bond in place to make sure that the mine site can and will be rehabilitated once the mining finishes. We always say in Ireland that before you open a mine, you have to know how you're going to close it.
But that didn't happen in somewhere like here.
That didn't happen here, and that's because this place has been operated since the 1700s. So when you have mining that has been operating for such a long period of time, you obviously deal with a lot more legacy issues. Today is quite a good day to see that. So you see all this water that's falling on this spoil heap, and that water is going to be picking up contaminants and heavy metals and the remnants of the minerals, and that will be running into the watercourses. This will need to be cleaned up at some point and to make sure that the water that comes off it and goes into the watercourses is properly treated and is properly looked after.
So tell me about remining.
Well, remining is where we go back to places such as Avoca and other waste materials and waste piles and look to extract the valuable resources out of them. We know we have elevated rare earth elements, which are really key to electronics. We also have silver within the ore here, which is key for photovoltaics. And we also have zinc, and zinc is obviously a key battery material, and it's also key for galvanizing, which really reduces the amount of steel that needs to be used. We know for the green transition going forward, we're going to need a huge amount more metals and more of these minerals. And so it's important that while we're waiting for new mines to come on stream, that we access the materials in alternative sources such as here.
Tell me about other mines in Ireland and how they're playing a part in terms of closing all the loops.
Well, the mining in Ireland is really taking advantage of this move towards a circular economy, and we see a lot of the historic mines such as Gert Drum down in Tipperary, and we see planning applications in place there for large solar panels. Then also in Tipperary and silver mines, we have a potential to turn the open pit there into a pumped storage solution. So similar to Turlock Hill, where we could have a huge battery that powers the entirety of South Tipperary. And at Galmoy, now that we know what minerals are more important and more valuable, we can see that Galmoy is now being reopened to take advantage of the minerals that weren't extracted when this was in operation.
Amazing. So you might come to somewhere like this and go, oh my God, what a pile of old rubbish, but actually there's loads of potential in it.
Absolutely. When you come to someplace like this as a geologist, you tend to get really excited. There is stuff of value here, and mining is really key to the circular economy. So we talk about reducing, reusing and recycling, and our mining for zinc really helps us to reduce the amount of iron and steel that we need worldwide. We know that we can recycle material here, and then we're reusing mine sites across the country for new and green projects.
Mining raw materials is essential, but we need to examine how we can maximise our use of those metals and minerals once we've taken them from the ground. Maria D'Souza Gallagher has been working on a novel technology that will allow people to mine electronic waste.
We don't recycle much. They say that in Europe we recycle around 40%, but in general is 80% of our electrical waste goes to incineration or to landfills.
I mean, when you think about like electrical goods shop and the amount of stuff that's sold and that 80% of it ultimately went up in landfill or incineration, it's kind of mind-boggling, isn't it?
It is. These materials include lots of important metals. Some of them can even be gold, tantalum, indium, and other components that are important. And if our resources are becoming scarce, we'll need to think that one day we might not have these components to continue living the way we are living today. We could continue mining them, but we can also do what is called the urban mining, that we are trying to recycle these components from the existent products.
Recycling products can be expensive and very labour-intensive, as components need to be separated into individual pieces beforehand.
The Recall project involves this novel multi-product recycling technology that involves one single unit operation that can recycle different products, and these are tantalum from printed circuit boards, indium from LCD screens, automobile shredded residues, and other composite materials like mixed plastics and laminated plastics.
Frank Riedewald has developed a reactor that allows the separation of different components from plastic waste that wasn't previously accessible.
Composite recycling is the recycling of composite materials. For instance, a lithium-ion battery is actually composed of aluminium, copper, plastics, and a black stuff where the lithium is in. This is so wound, so tightly together, you can't just unwound this. If you open a battery, there's no way that you can just simply take that apart. So this makes this very difficult to recycle. We invented a new process, and this process puts the battery onto molten zinc. That ensures that the heat transfer is extremely rapid.
If you're exposing something to such high temperatures, how do you actually retrieve the valuable materials?
If you put a battery onto, or any of those sort of composite materials onto molten zinc, what happens is the material floats actually on the zinc and it's extremely hot. The plastics evaporate, okay, and you free the other materials and you can recover all of that then separately.
Frank has taken me to see the prototype reactor and how it can be used to recycle batteries and other composite products.
This is the molten metal reactor. The molten metal surface is around that size in there, okay? This here is a lithium-ion battery. You can see here there's plastic, copper, aluminium, and then this black stuff. So this is what it looks like when you take it out of the reactor, okay, after the process. So you can see that all the plastic is gone, and you can open it and then separate the materials afterwards.
Once the plastic and solvents have evaporated, the battery can be unrolled, so the copper, aluminium, and the black material that contains lithium can be separated and recovered.
For printed circuit boards, we can do the same thing. And you can see here, for instance, these little pieces here, or the large ones here, these are tantalum capacitors. And we found a way to recycle the tantalum capacitors, which at the moment are lost in the recycling process, because people are only interested in the actual copper.
It's one single unit operation, can be scalable, so if you want more throughput, you just double the size. When we are designing these components, we need to design them having in mind how they could be more easily sorted, how can they be recovered, and what technologies will be available that can effectively, efficiently separate these components.
In our take, make, waste world, we sometimes forget that metals and minerals won't always be cheap or readily available. While the search for raw materials will always be necessary, urban mining could play an increasingly large role in the circular economy.